Okay, now let me maybe start by briefly talking about why are we interested in electronic excited states or electronic excitations. And what you'll be seeing on this slide as well as the next slide is that whenever we're looking at some research problem, one of the common themes is that we're always trying to understand some interesting physics aspect and connect it to applications. Okay, so then maybe if you see those pictures up here, the application that comes to mind, especially this material you probably have seen before, it's an organometal halide perovskite material that is used as photovoltaic. So I put photovoltaics here. That's the structure of the material, and this is maybe what the material looks like in real life if you make it. And as you can see, the optical properties, for instance, of this material there seems to be a certain variation in the optical properties. Right? And what we want to understand is how do the optical properties of this material, which are necessary to understand if you want to make a photovoltaic, how do those connect back to the underlying physics? And so for excited electron states, the physics that we're specifically interested in are, for instance, the physics of excitons. So I'll talk about this in a moment. And then you'll see as I'm presenting the framework that we're using, one of the problems that will occur over and over again is actually dielectric screening. So the physics of screening in the material determines optical properties, and that's something that we would like to understand. The other thing I put here, so I'll talk about bioimaging in a moment, but let's also briefly look at optoelectronics. And so what I'm trying to highlight is again optical properties of materials. And so the image that you can see up here is actually a computer-generated image, so that's not a photo. And what we used here is a ray tracer, right, to produce the scene. But the specific, the specialty about this image is that this is a so-called physics-based ray tracer, meaning we did not say make this cube orange and this cube yellow, but we put the actual physical absorption and reflection spectrum into the code that comes out of our simulations. Right? So in other words, you can predict what does the material look like if it has a certain optical, let's say, reflection or transmission spectrum. And so, for instance, these two cubes that you can see here illustrate what happens if you turn on and off excitonic effects in this perovskite material. Right? So you can see those excitonic effects actually have an impact on the appearance of the material. That does, by the way, not explain what's happening here, but that may be unrelated. And then one of the more recent applications that we've been looking at is we want to connect the optical properties of the material with the crystal structure. This example you'll see in a moment in more detail, where we're looking at cadmium selenide. And so I'll briefly just say what happened here. So in this case, we looked at two different crystal structures of the zinc oxide material. The wall-side structure is what you will find in an equilibrium sample that you grow. But in thin films, for instance, in nanostructure of zinc oxide, people also have reported this boron nitride structure. And so in this case, we studied the optical properties of both, and we can now optically distinguish those. By just looking at the absorption spectrum, we can tell whether the sample is made of wall-side zinc oxide or boron nitride zinc oxide. All right. So now, what about the time dependence? Okay, so then, as I said before, again, we're kind of combining applications and underlying physics. And so when we're now looking at a time-dependent problem, one of the things that we're always interested in is how materials interact with radiation, with particle radiation in this case. And so I'll play this movie down here first. So what you'll see here is a piece of aluminum. Okay, so this chunk here is aluminum. You can see all the individual atoms. The orange stuff is the electron density in the aluminum. And then this little dot that will start moving in a moment, if I actually get the movie to play, will now be impacting the aluminum, right? So when it hit play, the proton will shoot into aluminum, and then you'll look at the electronic excitations that emerge as a result of that, because it's already moving. So first it hits the material, not that much is happening. You can see maybe some small changes out here. But then after a while, the proton actually exits the material, and with it, a bunch of secondary electrons exit the material as well. Right? So the proton excites the electrons in the material, and they leave the material as a result. And the other thing you can see is the proton in the beginning was completely without an electron, was just a proton. Now it has this little shell around it, right? So it grabbed some electrons of the material and took the electrons outside of the material. So understanding these kind of processes, both qualitatively and quantitatively, that's one of the goals that we're trying to achieve. And so then the second example, you'll see that in more detail later. What you can see here is a magnesium oxide material. You don't see any atoms in this visualization, and all these spheres that you can see here are just isosurfaces of electron density of magnesium and oxygen. So let me play this movie. And in this case, we shoot a proton into this material. That's the example I'll show later. So here's when the proton comes in. Again, you don't see the proton itself, you just see the electron density change that it triggers in the material. So this blue bubble is kind of, it represents the change of electron density as the proton travels through the material. So this time dependence is what we're trying to describe. Application motivation for this is, for instance, developing radiation-hard materials, right? If you shoot a satellite into space, solar cells are subject to radiation. The computer in the satellite is subject to radiation. And so the electronics actually need to be radiation hard. So that's the reason why the satellites that we do shoot into space right now use chips that are very old, right? Because the older chips had larger structures, all the transistors were larger on the chip, and so any individual radiation event didn't trigger as much problems, right? Modern chips are more prone to that just because the proton compared to the structure of the chip is larger, right? And so one of the things, again, I didn't find, unfortunately, the reference, but at a recent conference where I presented, somebody in the audience said that as research has been conducted, that every 10% of all your Windows computers crashing is actually a particle from space hitting some memory and flipping bits. So again, don't quote me on it because I did not put the reference here. But this kind of research is being done. Like Cisco investigates it for their network routers and things like that. So anyway, the interaction of radiation and electronics is a problem. The other application could be, for instance, when you make a qubit, you want to implant certain defects in the material, and one technique that uses ion implantation. So meaning you shoot an ion into the material until it stops and creates maybe a defect that you use as a bit. In the physics, in this case, the first one I will talk about what I mean by electron-mediated diffusion, and then this stuff down here were the secondary electrons. You want to understand how many secondary electrons you get, for instance, for a certain projectile impact angle, let's say, and kinetic energy, and these kind of things. All right. And so the remainder of the talk, what I'll do is I'll start with time-independent excitations, right? So in this case, I'll tell you what single and two-particle excitations are, and the approach that we're using to study them. And I'll actually start with that. Now, many of you guys, probably the electronic structure people in the audience, will know these techniques because they, largely originated from places like Berkeley. And so the framework that we're using is many-body perturbation theory. And the way this is typically done in practice is a three-step procedure, which you can see on the top of this slide. So we go through 3 steps. The first one that does not have a box around it, because I will keep it very brief, is we need to know the atomic geometry. In this case, we just use density function theory along with maybe a local density approximation to minimize forces on atoms until they're in their equilibrium position. For the materials that I'll be showing you today, that works relatively well if you compare to experiment. Maybe deviations on the order of 1 to 3%. I'm mentioning it anyway because it's not a trivial problem in general, right? If you look at very complicated materials, that approach may fail. For the materials that I'll be showing you, that works actually pretty well. Now, what I want to focus on are excited electronic states, and so the second step in this 3-step procedure is the one that has a box around it, which is getting insight into the electronic band structure. Now, in order to understand why this is called a single particle excitation process, the way to think about this is the following. So if you're measuring an electronic band structure or an electronic band gap, what you do is you excite your sample, right? You shoot, for instance, an X-ray photon into your sample. And as a result, one electron is excited outside of the material. If you think of photoelectron spectroscopy, for instance, that's exactly the process that happens. And then you detect the kinetic energy of this electron, right, in PES. What it means from the sample's point of view, the sample lost an electron and is now in an excited state, right? And it lost 1 electron per photon, so that's why it's a single particle excitation. I will contrast that to optical properties in a moment. The approach that works to this, so density function theory does not work well for that. Again, that's something that's very well known in the literature, but many-body perturbation theory is the approach that we're using. And in this technique, what we have to do is we have to solve this quasi-particle equation given here. So it's a Dyson equation. It has maybe, let me say, 2 terms here, right? One is this first one over here, which is a single particle-like term with the kinetic energy of electrons, the external potential, which are the ions acting on the electrons, and then a Hartree electron-electron interaction. Okay, so just Hartree. That is the easy term. The more complicated term is the second term, which has this sigma expression. Right? Sigma is the electronic self-energy. That describes all electron-electron interaction beyond Hartree. Right? So the quantum mechanical electron interaction specifically, and that makes this equation complicated. So you can see it's non-local from this R and R prime index here. Right? That makes this term complicated. And in addition, it depends on the solution. Right? So this self-energy here depends on the solution of the equation. So we have to solve it self-consistently. Now, one thing that may already be clear at this point is we have to make approximations. And one very common approximation in literature is the so-called GW approximation. Again, there's a lot of history of this in Berkeley, so if you're bored by this, maybe bear with me until we're at the next slide. In any case, we approximate this expression, the self-energy expression here, as the product of the Green's function of the electrons and the screen-Coulomb interaction. So I'll say this one more time later. This W term is the screen-Coulomb interaction between electrons in the material. So screen meaning W is the product of the bare Coulomb interaction without screening divided by the dielectric function of the material, meaning the response function of the material. Okay. So if you make this approximation, we still have to solve the equations up consistently, meaning it is still numerically expensive to do that. And instead, what people oftentimes do in practice, they do a perturbative treatment, where they come in with a reasonable starting point or initial guess for epsilon and psi as an electronic structure, and then do one step of perturbation theory to calculate corrections that emerge from this equation. For that to be valid, as you know from your quantum mechanics class, for one step of perturbation theory to be valid, the starting point needs to be kind of close to the final answer. And for the materials that I'll be showing you today, usually what happens is if you use a hybrid functional to describe exchange correlation, that gets you epsilon and so quasi-particle energies and wave functions that are reasonably close to the final answer. So that's what we do as the input. So what I just said is how, I guess in the next couple of slides, is shown as figures, right? So let's say you start with density functional theory, you calculate the band structure of a material, in this case zinc oxide. What happens is, the band gap is too small, right? Again, that's known in the literature. In a specific example for zinc oxide, you find 0.7 electron volt as opposed to 3.4 in experiment. So that's dramatic in the sense that if you're trying to explain optical properties of the material, and you know the spectral range is between 1 and 3 electron volt or something like that, this underestimation is of course not acceptable. So the band gap is a problem. And then the second issue that occurs is that these D states, those are zinc D levels, these flat bands here that I'm trying to highlight, with my dying pointer. I don't know if you can see them. Yeah, pointer. So those D states occur too high in energy, meaning too close to the Weierstrass maximum. Alright, so this is not that close to the final answer, which is why TFT is not a good starting point for this one step of perturbation theory. Thank you so much. That does look like I just do this. Okay, well, I'm not listed. You can probably see it again. So now, what I'm trying to say is, if you use this hybrid functional, we improve that starting point. So now these red curves show the result for the hybrid function calculation. In this case, we get 2 electron volt versus 3.4, so that's closer. We use that as the starting point for these for this GW approximation. In this case, we end up with 3.2 electron volt. I'll try all of them. Perfect. So this is not on top of each other, but that's much closer, and that's something that we would call a satisfactory input for our third step that I'll be talking next, which is calculating the optical absorption of the material. Okay. Now, before I do that, I want to, I guess, make the point that an optical absorption experiment is different compared to what I just talked about, in the sense that that will be a two-particle excitation. Now, why is that? So in an optical experiment, in which case, maybe look at this cartoon here first. What I show you here is the valence band of the material. This is a cartoon, so it's just a two-band model with parabolic bands. But what happens is in an optical experiment, you come in with a photon, you excite an electron out of the valence band into the conduction band, but not outside of the material. Okay, so that's the big difference. So now after the excitation, you have two excited particles in the material. Right? You have this electron, you have the hole, so it's two-particle excitation. And the reason this matters is they're oppositely charged. And so they interact with each other. And that is something that the single particle picture that I just described does not account for. Right? So in other words, we have to go one step further in this framework of many-body perturbation theory to capture this interaction of these electron hole pairs. Okay, again, many-body perturbation theory has been developed for many years, and the approach to use in this case will be, it's called the Bethe-Sapir equation. So it's an equation that describes the optical polarization function, taking into account the electron hole interaction. So the equation itself is given in this box. If you've never seen this equation before, don't be confused by this notation. This is this 1 and 1 prime and everything. This is just shorthand notation that one of these numbers represents the position and the time coordinate. The critical point is actually that the electron hole interaction here occurs as the kernel of this integral equation. And the way to go to something you can measure would be to solve this expression down here, which uses the polarization function and the Coulomb potential to get epsilon, which is your dielectric function of the material, and that is something people can measure. As I said earlier, people who use ellipsometry, for instance, can measure epsilon directly. So that's what we want. In practice, the way it is done is this expression is rewritten as an eigenvalue problem, which is my last equation on this slide, and we call that an eigenvalue problem for an exciton Hamiltonian, which is this Hamiltonian. And maybe I will just briefly talk about the structure of this Hamiltonian. So it has a diagonal term here. You can see the delta functions to say it's the diagonal. And you have a difference here of these single particle excitation energies. So this is where we put our input electronic structure from, let's say, for instance, hybrid function calculations or something like that. These epsilons go here as single particle excitation energies on the diagonal of the Hamiltonian. But since it's a two-particle excitation, you have off-diagonal elements. And you have these two specific terms here. One is an unscreened Coulomb potential, so this is taking into account local field effects. And then you see W again. So W is, as I said before, the screened Coulomb interaction. Okay, so these two are the off-diagonal. So what we do in practice is we compute this Hamiltonian using wave functions and single particle excitation energies and evaluating these matrix elements. Then we either diagonalize it or we have a time propagation technique that gives us a spectrum. Let's say we get the optimal spectrum, so we want epsilon. That's what I'll show you next. So we solve the Hamiltonian, or we set up the Hamiltonian, then we calculate epsilon from it, and then we compare to experiment. So this is an example for magnesium oxide. So what I plot here is the imaginary part of this epsilon quantity as a function of photon energy. And you can see two curves here. One is the black curve, that's an experimental result for magnesium oxide. And then there's the result that we would get if we do not take into account this electron hole interaction. The good news is that the absorption onset actually kind of agrees, right? If you look at where the position of the gap is, that is very close. That is because we use this HSE plus UW technique to get these single particle excitation energies. The problem is, starts right after, right? So as soon as you go to a little bit higher energies, you can see there's basically no agreement between experiment and the calculation. Now we know what the reason is, because if we turn on these excitonic effects, we get the blue curve, everything else being the same in the calculation. And the reason I'm showing you this is, you will see two effects here that are very universal for many semiconductors. The first thing is that directly at the absorption onset, you see this very sharp peak here that appears in the blue curve that's not there in the red curve. So this is an excitonic bound state. That occurs because the electron hole pair have a finite binding energy, and they have, so that tells you where it appears in the spectrum, and they're strongly bound, so you get a very sharp peak in this absorption curve. So that's something you see for many semiconductors, the occurrence of bound states at the absorption onset. The other thing that appears is this so-called redshift. So if you look, for instance, at this peak here in the red curve, it appears at slightly lower energies once you include electron hole interaction, right? So it shifts to red. That's the same for this peak, it's the same for this peak. So that's again a kind of universal effect that we see for many semiconductors. If we now compare to experiment, you can see this is much better, that's a much better agreement, right? So the fact that it's in such good agreement, if you look at these two curves, that depends a little bit on the material, but in general you find that peak positions come out pretty well from this framework, and even relative peak heights. So now, again, I guess the point I'm trying to make here is, if two curves between experiment and theory look like this, that's what we would call good agreement, right? So you see they're not on top of each other, but that's not the goal, right? We're trying to explain where it's coming from, and in this case that's something that we would call good enough agreement to draw conclusions about the material. Alright, so now I will show you one application where we use these techniques to actually learn about the crystal structure of the material. And in this case, I will talk about semiconductor nanocrystals. And before I talk about nanocrystals, I talk about bulk material. The bulk material in this case we're looking at is cadmium selenide. That is motivated by a collaborator in bioengineering. They want to use nanocrystals for bioimaging, meaning they want to put it into your body and then maybe detect whether there's cancer or not by using fluorescence of these nanoparticles. But before they can do that, what they need to know is whether the nanocrystals they synthesize in experiment are either zinc blende structure or Wolfside structure. So those are not that different, but they're different crystal structures. And so the question that he had was whether we can distinguish zinc blende and Wolfside optically. Okay, so the first thing we did is, because it's the easiest thing to do is we looked at bulk cadmium selenide. Okay? And so you see four curves in this figure now. So what we plot here is, in this case, absorption, which is not exactly epsilon, but we can calculate that from epsilon, as a function of photon energy. And you see four curves because we again compare calculations with excitonic effects to calculations without excitonic effects. And we also compare both crystal structures in both cases. So maybe let's start with, which one will we start with? Maybe we start with one with excitonic effects, because I said that those are generally important in semiconductors. If you look at red versus green, you can see that at the absorption onset, you cannot optically distinguish them. Two spectra look very similar. But at higher photon energies, you can see that the zinc blende peak, this peak here, occurs earlier in energy than the Wolfside peak. Okay, so this is actually what triggered this whole study that then emerged, because this got Andrew Smith excited when he saw that. He said, we can now measure at two different energies. We look at the relative intensities and we know whether the sample is Wolfside or zinc blende. Okay, so then the problem, of course, was this is bulk material, not a nanocrystal. And the second problem is, these calculations with excitonic effects from many-body perturbation theory are expensive, meaning we cannot simply study, or not easily study, nanocrystals, because that makes the calculations a lot more expensive. We need a large supercell with many atoms, so that makes it computationally challenging. And so the first thing we did is we checked what happens if we turn off excitonic effects. Now in this material we were lucky because what you can see is if you compare, let's say for instance, the green curve, which is zinc blende structure with excitons, to the bluish curve here, which is zinc blende without excitons, the general trends remain the same. So the absolute height is a bit different, okay, but the fact that this peak here appears at lower energy than the same comparison for the wall side structure, that for instance remains the same. And so we use this to motivate that we can actually use only density function theory calculations for nanocrystals. Now you ask probably, well, after talking about the importance for exotonic effects the entire time, why do we now neglect them? Well, in this material that's actually justified and we know why. And the reason in this case is, compared to magnesium oxide, the electronic screening in platinum selenide is much, much larger. Right? If you look at dielectric constant, magnesium oxide is something like 3, platinum selenide is something like 14, and the importance of exotonic effects scales quadratically with the inverse of the dielectric constant, meaning a material with a large dielectric constant has very little exotonic effect. So this actually physically motivated the fact that we can neglect it here. All right. So now what's left to do is actually use this technique without excitons to calculate absorption spectra of nanocrystals, and so we did that next. And you can see, I guess, 5 different crystals that we studied. Right? We look at pure zinc blende, we look at pure wallsite, and then we have a bunch of cases in between where we have nanocrystals that are partly zinc blende, partly wallsite, and the way this is done is by introducing a stacking fault that separates areas of crystal structure of one over the other type. And so we can basically change the wallsite percentage if we do that. If we now look at the absorption again, which is what we plot here as a function of photon energy, you can see that the trends that we saw for bulk actually still appear here. Meaning at the absorption onset, they look very similar, actually, independent of how much wallsite is in the sample. But if you go to high energies, you see again the fact that the zinc blende peak occurs at low energies than the wallsite peak. And then the other thing you can see is this ratio sort of scales with the percentage of wallsite. So you can even do this semi-quantitatively, but you can certainly do it qualitatively. So that's now something that Andrew Smith wants to use in his lab. So at this point you may ask, well, okay, what is the big deal then? These techniques seem to work pretty well, so what's the problem with those? Okay, so for that I just compiled maybe a couple of central equations that I showed you earlier. So you can see where we calculate these band structures using the GW approximation, we calculate excitonic effects using this Hamiltonian that has W in it, right? That one of the ingredients is W. So W is actually what we found to be very tricky. In other words, the results from all these techniques depend sensitively on what we use for W. Now, why am I saying use here? Well, I'll give you two examples where this becomes a problem. And the first example is actually shown on this slide here, which is indium oxide. So this is now a material, it's a transport conducting oxide, right, cubic structure, and we calculated again the optical properties of the material. So maybe just for now look at the red solid curve, which is this framework with excitons and correcting the band gap and everything, and compare that to the black curve with the experiment. So if you start, let's say we start at high photon energies, right, so they agree pretty well, very close to each other, up until you get to the onset, where you can see that in this case we overestimate the value of the imaginary part of epsilon by quite a bit compared to the experiment. Right? So this difference is now what started, it didn't start it, but what confirmed our suspicion that there may be a problem with the screening. We've seen similar trends for many of the other oxides. Every time we go to the to the absorption onset, or we look at an exciton binding energy at the absorption onset, we overestimate the strength of excitonic effects in our framework. And so now we started questioning, because we don't really have knobs in the framework that we can tweak, right? So we're trying to figure out what are we missing. And so I'll show you two examples where this epsilon is indeed the quantity that needs to be improved. The first example, before I actually come back to this, is doping. So if you dope a material, this is what you do with pretty much all semiconductors, otherwise you wouldn't be able to use them for conducting electricity. If you dope a material, so this first I start with the undoped cartoon, you've seen that before, right? This is our undoped material. If you dope it, two things will happen. You dope it so that you get 3 electrons. Let's say you dope it n-type. This is, I guess, what this slide is for. So you just dope it n-type, you want 3 electrons in the conduction band because of donors. What happens is you will end up with 3 electrons in the conduction band. This is shown by this little gray area here, which indicates now occupied conduction band states. For the optical properties, what that means is they will shift the absorption onset. Why is that? Well, because you cannot absorb here anymore, right? Because this electron up here has no empty state above it. So that absorption is blocked. That's called Pauli blocking, and it leads to a so-called shift. It leads to a shift in the spectrum that's called the Burst-Reynolds shift. Okay, so that's one thing we need to account for. The other problem, and that goes back to W, is screening. So free carriers in the material, even if you have just a certain, you have a certain concentration of these free carriers in the conduction band, they behave like free electrons, in the metal with a certain concentration. Those can respond to an external electric field, meaning they contribute to screening. So that needs to be taken into account. And in the literature, people who strongly pump semiconductors with intense lasers, for instance, they've also looked at this contribution, and they even said that for very high concentration of these free electrons, the electron hole pair may unbind because you have a large additional screening contribution. So that's what we need to take into account in the framework. And it is not included normally in this framework. All right, so that's, I guess, what we're now trying to do. And so on this side, I'm showing you the results for that. We've done this actually a couple of years back. And so what we did is we included this bursting Moss shift simply by taking into account your occupation numbers of conduction band states if you have a certain doping concentration that we can simply do using the band structure. And we also included this additional screening contribution. And in this case, we used free carrier screening. So we get some intra-band additional contribution using a Lindau dielectric function. You end up with this analytical equation here, which has a Thomas-Fermi weight factor. And this is the quantity where we capture your materials properties, meaning NC is now your concentration of free electrons that you have in the material, your doping concentration if you want. We have the background screening in material, and we know the Fermi level of those free electrons. So we implemented that into the W term of the excitonic Hamiltonian, right, on top of the electronic and interband transition. So then we calculate optical properties. In this case, we're looking at zinc oxide, and you can see two figures here. We can really just look at either one. Maybe we use the bottom one. So this is for a specific experimentally achieved doping concentration, in this case 4.8 times 10 to the 19 inverse cubic centimeter. And we compare, so the green curve is our computational result, the green solid curve. The black solid curve is the undoped material. So in this case, you see your bound excitonic state again. And then the data points here, that's the experiment. And so what you can see is if we include these effects, this bursting Moss shift, as well as the additional screening contribution, the curve shape changes tremendously, right? So the additional screening lowers your exciton binding energy so much and the oscillator strength in the spectrum that you don't see this bound state anymore simply because of these free carriers. So that shows that you need to take them into account. Compared to experiment now shows very good agreement. And so in the literature, this was discussed, I guess, in the 1960s by Mahan, right? You guys know probably his book. And in the 60s, he had a paper where he used a two-band model, and he studied that analytically, and he showed that the binding energy in this case goes down exponentially with the doping concentration. So that's what, that never becomes zero, but it goes down exponentially. So that's why these effects are called Mahan excitons. Okay, so now what about this indium oxide example? So I guess the case I'm trying to make, and I will show you preliminary data because this is ongoing work, but the case I'm trying to make is in materials that we call polar materials. So those are materials where, in addition to an electronic response, your lattice is also very polarizable. In those kind of materials, it's not sufficient to just use electronic interband transitions to describe your screening function. Okay, so what does it mean in a cartoon picture again? So what I show you here is the real and imaginary part of the dielectric function. In this case, not a dielectric function that we predict or that we put into the code. This is just an illustration of what the dielectric function looks like if two response mechanisms occur. So the normally accounted for response mechanism in this Bethe-Savino framework is electronic response, meaning electronic interband transitions. So you know that those occur at or above the band gap of the material. Okay, so let's say, for instance, 3 electron volt. And in this cartoon, I just show you here one oscillation. It's a single oscillator model for that in the imaginary part. So this is electronic response. In the real part, what you get is the chronic transform of that. Right? So you have this oscillation. Now in the polar material, you also have a significant lattice response. So that would be your second oscillation. That occurs at phonon, let's say, longitudinal optical phonon type of frequencies, so much lower in energy, which is why it appears over here. But you have some response there. And for the dielectric, for the real part, that again means you get none of these oscillations. And so if you now look at this overall real part, what you can see here is there are now two values of dielectric constants. The epsilon 0 is the zero frequency dielectric constant, including the lattice contribution, right? It's somewhere here. And then we have epsilon infinity, which is the high frequency dielectric constant from the lattice point of view. That's where the name comes from. Epsilon infinity indicating high frequencies. High not meaning infinity frequencies, just high compared to phonon frequencies. At the same time, this is the low frequency response from the point of view of the electrons. Right? If you go down to, if you come from an electronic response energy, you go down, you end up at this epsilon infinity value. And you can see you can see it in the cartoon, but I'm also trying to explain that in the polar material, these two numbers are very different. Right? So meaning you have a large epsilon 0 and a not so large epsilon infinity. For instance, in magnesium oxide, the difference is 3 for epsilon infinity and 6 for epsilon 0, something like that. So my point is now, in those polar materials, we need to take into account this lattice response. At least we're exploring whether we need to take into account. As I said, this is preliminary work. And so what we now do is we're trying to include this lattice contribution in the dielectric function that we use to screen the Coulomb interaction. This has been done for GW calculations before by other people. Right? They found that the band gap is significantly affected by it. What we want to see is we want to check whether the optical spectrum is also subject to such a change. Okay. And so what we did so far is we replaced simply the electronic dielectric constant in our model dielectric function that we use to calculate W in those calculations. Instead of using the electronic dielectric constant, we use the epsilon 0. That's as far as we got so far. And so what you can see, this figure is exactly the comparison between those two cases. So the red curve you've seen before, the black curve you've also seen before, because that's experiment. And the blue curve is now what we get if we include this lattice contribution. One disclaimer though, we currently included incorrectly because we just replaced one dielectric constant with another. So we know that that, for instance, does not give the correct Q dependence. That's something that Josh is currently working on. But if we do that, we get a limiting case. We get a case where we overestimate the lattice contribution. Now what happens to the spectrum? Okay, so at high energies, not much, right? You can see red and blue are very close still. At low energies though, the blue curve is now much more reduced, right? It's much closer to the experiment, sometimes maybe even underestimating the experiment, depending a bit on the frequency. But in any case, this additional screening gets us in the right direction. And so this now motivates to actually fix the wave factor dependence, take into account correctly. That's something that, as I said, Josh is currently working on. All right, now let me actually spend some time. Okay. When am I supposed to finish? Soon?
Around one, yeah.
All right.
15 minutes left.
Okay, good. Yeah, that's good. So let me briefly talk about also the time dependence of these excitations. And so before I actually start about an application, which will be this magnesium oxide example, let me briefly talk about the framework that we're using and also motivate why we're interested in this work. So the motivation itself comes from interaction of radiation with materials. So I mentioned this electronics in space kind of problem. You know, people use particle beams like protons, for instance, to treat tumors. So in all those cases, you really want to understand in great detail how the particle loses its energy as it is inside of the material. And so the way we typically look at this is we divide this into different energies. So we use the energy of the incoming particle that you shoot into something or that gets, that hits solar cells, for instance. We use the kinetic energy of that particle as the x-axis, and we look at the energy that it loses per distance traveled as the y-axis. So that's called stopping power. It has the units of force. So that's kind of like a friction force if you want. If you're a proton, you're moving through material, you experience friction. That friction force is the y-axis of this figure. And what this figure is supposed to illustrate is that there are maybe two distinct energy regions for the projectile kinetic energy that allows her to split this into an ionic contribution, meaning in this case the proton or the particle predominantly interacts with the lattice of the target material. That's at low kinetic energies. And then it also, if it's faster, actually can interact with the electronic system of the material, meaning it loses energy directly to the electrons. That's the regime we're in this talk, anyway. Right? So we want to look at this electronic stopping contribution. So a case of a fast projectile hitting the material and dumping energy into the electronic system. Okay. Questions that we're trying to answer. So in general, we want to understand radiation damage, but specifically what has been observed is that radiation can do two things in the material. It can cause damage because we have an energetic projectile, you kick ions around, that causes defects. At the same time, the lattice heats up, and so you can anneal defects also. So both effects are reported in the literature. And another effect that was observed that motivated the specific study is that if you have a defect present in the material and you come in with radiation, new defects predominantly form close to the existing defect. So in other words, we wanted to look for a mechanism that could explain the fact that an existing defect acts as a nucleation site for more defects. Okay, so that brought us to the study of magnesium oxide. The framework we were using in this case is not being body perturbation theory. In this case, we're using time-dependent density functional theory. Meaning, we use the time-dependent version of DFT. These are the corresponding equations, right? So the time-dependent quantum equations look like this. The Hamiltonian in this case, again, we have kinetic energy term, we have the Hartree electron-electron interaction. So it's DFT, right? Meaning our everything beyond Hartree is now in an exchange correlation functional. So for this we use time-dependent local density approximation in these calculations. But we also have this external potential, and that is not time-dependent, right? So we want to look at some time-dependent excitation. The time dependence here comes from this moving Coulomb potential of a particle, right? Remember this proton that we shot into the material in the very introductory slide, that proton moves, so that's a time-dependent potential if you're an electron. Okay, so then technical details I have some here. So we use the systems we're looking at in this talk are periodic materials like magnesium oxide. So we use plane wave basis functions for that. The electron ion interaction, for that we use normal conserving pseudopotentials. That's a standard technique. As I said, we use chemical and LDA. And this is something we implemented into this Q-ball code, which is very parallel. So that started when I was in Lawrence Livermore. They wanted to run on very parallel machines, and they had the Q-ball code, which was a time-independent DFT code, plane waves, and so we implemented the time dependence basically. So now what you have to do is, the last thing I should say, time-dependent DFT, anyone in the room who has run those calculations probably knows that you can calculate spectra from it by making the linear response approximation. So that's not what we're doing here. In this case, we're using, so there's another flavor of time-dependent DFT, which is called real-time propagation. That's what we're doing. So we start with an initial condition for these equations that comes from density functional theory, and then we propagate in real time, going from time step to time step to time step. So we propagate these orbitals in real time. That in itself is actually an issue, and it's an unsolved issue, meaning many people are trying to find integrators, numerical integration techniques that can achieve that, right? So that can achieve this time stepping of these equations. Including people here, like Lin, for instance, at Berkeley, is looking at the ways of doing that very efficiently in math. So this is an applied math problem in some sense, to efficiently propagate those equations. Early on, we started with a Roman-Kutta integrator, fourth order Roman-Kutta integrator, that worked very well for plane waves. The problem we found is that the error is relatively large, the numerical integration error, and so then these guys at Lawrence Livermore implemented this enforced time reversal symmetry technique, which is an implicit propagator, so it depends on the solution of the equation to the electron density, and so you need tricks to do that. But it conserves energy very well, and it conserves orthogonality of the wavelengths very well. So it reduces the numerical error. And the other thing is, I'll show you this very briefly, but what this also does, it scales very well. So this is a test they did at Lawrence Livermore, where they visualized the petaflops that the calculation, at which the calculation ran, as a function, of course, on one of their machines. I think this is on the Sequoia machine, which has up to 1.6 million blue gene cores. And so what this figure now shows is, so just to be clear, this dashed line here is ideal scaling, but ideal scaling for the blue and black curve, right? Otherwise you would claim that we're better than ideal, so that's clearly not true. So you can see two different system sizes in one figure here. But in any case, what this shows is that the scaling is actually not that far from ideal if you compare, let's say, black to the dashed line. So you can get very efficient calculations. Costly calculations though, because you need large computers. And so the applied math problem that I want to at least briefly mention, because Alina is working on that, is we want to see if there are better integrators that can get to the solution faster, right, at a certain error. And so in order to look at that, Alina came up with this figure of merit here, where she looks at, so she takes four quantities into account. The small caps dt is the simulation time step. That's typically an attosecond in our simulation, on the order of an attosecond. The d capital T is the wall time that it takes to perform one of these time steps with a given integrator, so the computer time in other words. And then we know that an ideal integrator would have no charge, would conserve charge and energy. Okay? And so any error in this charge and energy conservation goes into the figure of merit and diminishes it. Okay? And so what she now does is she plots this figure of merit as a function of the simulation time step for different integrators. So you can see fork is fourth order Roman-Kutta, ETRS is this enforced time reversal symmetry scheme I talked about 2 slides ago. And then there are other strong stability preserving Roman-Kutta method that she compared to. And what she basically finds is that the fourth order Roman-Kutta performs worst on this scale. The strong stability preserving schemes are in between. And this enforced time reversal symmetry integrator right now is actually the best one we've implemented. Meaning for a given large simulation time step, so you should not just look at the maximum of this figure of merit, because it's clear that as you reduce your time step, you conserve energy better, but it makes the calculations more costly, right? Because your time step is small. And so what we ended up doing is we used this integrator and at this time step, for instance, for a graphene cell, which is just an example. But in any case, we're trying to figure out if there are schemes that are better than any of the ones that are shown in the figure. That's an alternative to what Lin does, where it uses a gauge transformation to get to larger time steps. Okay, so now what I want to show you at least briefly is this hot-electron mediated ion diffusion magnesium oxide. So I guess we talked briefly about visualization and its importance. So this picture actually that Cheng Wei made got on the cover of Materials Today because they have a cover competition. So they, in this case, I'm always making fun of this a little bit because this is really just a beauty contest, right? The science itself doesn't matter for judging whether you got on the cover or not. It's just the image that matters. But illustrating your simulations in a nice way and using good visualization is important because this is how you sell stuff to people and talk about your science to people. Right? Anyway, so that's Schenkel was very happy about that. But I will talk now about the science and not as much the image. So what we started now doing is, okay, we built our magnesium oxide cell, which is just all rock solid structure of magnesium oxide, and then we shoot a proton on this black trajectory here, right? So this is the arrow kind of indicates the trajectory at which we move this proton through the material. The first thing we looked at is the stopping power, right? Remember friction force that the proton experiences in the material as a function of the kinetic energy. And what you can see here is, so let's look at, so first of all, the red curve is from an online database, so that's called the stopping range in materials. That's based on experiment, and you can download the data points, and you can use that as a reference. So the red curve is our reference, this SRIM reference here. And then you can see that, or maybe, let's look at the black and the blue curve. So if you start, the black curve is what we get if we do exactly what I just said, we shoot the proton with this trajectory. So we underestimate the stopping from the reference by quite a bit. If you go in an off-channeling trajectory, which means you just shoot the particle in a random direction through the material, you get much closer. And we can actually explain that that comes from the fact that the particle that's on one of these channels never really interacts with any core electrons of your target material. It's strongly tightly bound core electrons. Because it's just too far from them, right? The proton on the black arrow, it never gets close to any of the atoms. On the random trajectory, that's different, and so that's an additional loss mechanism for the proton. Okay, so that was our starting point. Then we did, we actually want to look at diffusion, right? That's what I'm trying to get to. And in order to look at defect diffusion, we first have to create a defect. Okay, so we did put an oxygen vacancy into the material. And what you can see now in the background of this figure is, oxygen and magnesium atoms, and this red blob. What happens if you create an oxygen vacancy in magnesium oxide? You get a localized defect level somewhere in the middle of the band, right? In the ground state, that defect level is occupied with 2 electrons. This blob is the electron density of that defect level. Okay, so you can see the vacancy here. And then we shoot the proton in. So this black arrow again indicates the trajectory of the proton, and we plot the occupation number of the defect level as a function of proton position. Okay, as I said, in the ground state, defect is occupied with 2 electrons. That's why everything starts at 2 here. Now let's say we shoot a very slow proton. Let's say this red curve here. What happens is, okay, projectile approaches the vacancy, it interacts with the vacancy, so the occupation number drops, but as the proton leaves, the occupation number basically stays 2. Not quite, you can see there's a little deviation here, but it's large again. Same happens for a very fast projectile, right? 2.5 atomic units of velocity, almost doesn't interact with vacancy at all. But there is a velocity range for the proton at which it really can excite the vacancy defect. Right? So you come in at 2, deoccupy the defect, and let's say for instance this black curve here is maybe the most dramatic case. You unoccupy the vacancy level and it stays unoccupied even if the proton moves away. So the take-home message here is twofold. First of all, there's a large, strong dependence on velocity. Okay, so that's what we'll look at that in a moment. And we excite the vacancy. So the first question that you may ask after this is, well, where does the electron go? Right? Because it's not in the vacancy state anymore. That you can see from this figure. Right? The occupation number dropped by 1. So to answer where the electron goes, what we did is we plot again occupation number, but now of all the orbitals in magnesium oxide, not just the defect level. So the x-axis here is the Cohen-Shannon eigenvalue. We put the valence band maximum at energy 0. So everything to the left is valence states. You can see those are still mostly occupied. And actually, I should say, the figure on the next slide is at a time where the proton is far from the vacancy, right? Somewhere over here. Okay, so then here's your vacancy level, right? It's now unoccupied by 1 electron, so 1 electron is still in it. That's because what the previous slide told you, the proton comes in, excites an electron. And then we see that there are a bunch of conduction states that are also occupied, right? So specifically these 3 guys here have now significant occupation number. The total sum is 0.72 in this case, so almost 1 electron, 3/4 of 1 electron. And if you plot the density of those levels, the partial charge density, you can see those are actually excited states of the defect, right? They look like orbitals, like 3 orbitals almost of the oxygen vacancy. So what happens is the proton comes in, excites the defect into an excited state. Okay, so now what we want to know is what's the influence of this excitation on defect diffusion, right? Remember, I'm trying to get to the point where we want to explain why, if you have an initial defect and you irradiate, why do you get more defects predominantly in the area or in the position where the defect originally was. The problem that we're facing is, in order to look at defect diffusion, as you probably know, compared to electrodynamics, those are 2 very different timescales. Right? Electrodynamics happens on the order of femtoseconds, maybe picoseconds, but defect diffusion is very slow compared to that. Right? It could be nanoseconds and much more. So we cannot simply run those simulations for longer and see diffusion happen. So that doesn't work. What we did instead is we use a transition state theory, which is a technique, if you look at defect diffusion, even without hot electrons, that people use, right? So there's this transition state theory that relates the diffusivity in the material, D, to a bunch of geometry factors. Like those are determined as soon as you know we have a rock-solid material, we have a certain number of defects in the material. This determines these blue factors, so those we treat as constants. And then you have a certain rate over here, right? This rate of diffusion. And that's this product. So it's a product of an attempt frequency, which is explaining how many times does the diffusion attempt to happen, and an energy barrier. We have this Arrhenius type law here with an energy barrier for diffusion and some temperature. Okay, so that's the theory that we're using, right? We use the natural elastic band technique to calculate the energy barrier. And in this case, we use 3 images. You can see starting point is when the defect is here, the vacancy is where my pointer is right now. Transition state is when one of the neighboring oxygen atoms tries to diffuse there, and the final state is when when the diffusion has completed. So we calculate the barrier for that using this natural elastic band technique. And you see 4 curves here. The black curve is what you would get if you do ground state calculations, no excited electrons whatsoever. So you get a barrier of something like 4.3 eV. And then we have 3 different ways of including the excited state effects. So the first thing is you may say, okay, proton comes in, you get hot, it excites electrons, those electrons thermalize, and you have now hot electrons in the material with a Fermi distribution. We can do that, right? So we can calculate how much energy is dumped into the electronic system. What temperature does that correspond to? In this particular case, 9,000 Kelvin, electronic temperature, right? Not that temperature. And then we fix those occupation numbers, we calculate the barrier. That's the green curve. So meaning, what you see here is it lowers the barrier a little bit. The other technique that you can use is, this is motivated by a model that the literature is, well, you've seen that the defect is charged, right? We have we took an electron away. So that's actually a model that is in the literature, the charge defect model for these events. So what we did is we fixed the charge state of the defect by saying, okay, it's reduced by 1 electron. What that does is, it reduces the barrier by quite a bit more. That's the red curve. Alternatively, what we do is, well, we have the actual occupation numbers, right? Those come out of our simulation. And so what we did is we fixed those in the natural elastic band. We just imposed those occupation numbers out of this TDDFT simulation. That's the blue curve. So that lowers the barrier even a little bit more. Now, what's the message from this? Okay, so you see that the diffusion barrier is reduced by, I think the number is here, 1.3 electron volt. So it's significantly reduced. Because it enters exponentially into this rate, that means that the diffusivity itself would be tremendously increased. Now the problem is, of course, in a real material, not all the defects will be hit by protons all the time. Right? We have sort of defect distribution, and radiation is only part of the sample. And so we use the rate equation to estimate whether under typical proton irradiation conditions, which in this particular case means 1 nanoamp of current, what would be the vacancy concentration that we would need to actually get a doubling of diffusivity. Okay? And what we found is in this case you would need 10 to the 13 defects per cubic centimeter, which is not nothing, but it's also not crazy. So that's something that can definitely occur in a Mendelssohn oxide cluster. So in this case, you would observe that diffusivity should be enhanced by a factor of 2 under those conditions. So that's something that you could observe in experiment. And so now we're trying to find experimentalists that kind of could verify that. That would be great. You can look at this 2 ways. You can either say we treat the beam energy and we look at a thin sample and see if we find an enhanced diffusion, right? Because it's very velocity dependent. Alternatively, you can say we come in with very high kinetic energy of the beam, and that is, as the proton moves through the material, it slows down. And in other words, there is a certain part of the sample where it has the right energy to enhance diffusion. So in other words, you should observe position-dependent diffusivity. So both of these techniques could be helpful to see this in experiment. All right. Now, before I stop, I want to emphasize one thing. If you like these kind of techniques, right, excited state techniques, or even time-dependent density function theory, next summer we'll run a workshop in school at Rutgers in New Jersey. So there will be the school first, which is from August 4th to August 9th, and then the workshop right after, where our students are encouraged to stay. So we'll have hands-on sessions. We'll have lectures in the morning, hands-on sessions in the afternoon, where you learn those techniques, probably using NERSC supercomputers. We'll try it. We did that last year. And then right after there's a workshop with more people coming in and giving presentations on their research. So there's currently, the website is a little bit early, but keep that in mind. If you're interested in those kind of techniques, consider applying and come to the school. And at this point, I will show you my summary slide. So I hope I could convince you that excited electronic states and real-time dynamics are important for applications, and they connect to exciting physics. I started by telling you that we can actually get an accurate description, for instance, for these nanocrystals, but also to highlight that more development is needed. Like if you, for instance, look at this lens polarizability, we need to describe that better in the framework. And then I also showed you that we can use these techniques to study, for instance, the effect of radiation on materials, and we believe that we found this hot-electron mediated mechanism for diffusion in semiconductors. At this point, I'll stop, and thanks for your attention.
Time for a couple questions, anybody?
So, for your nanocrystals,
Yeah.
I was wondering a simple explanation for why the zinc length versus wood side doesn't change so much, especially for the presence of the surface. And also, it's combining energy with the effect.
Right. So, well, I guess the reason why I think the spectra are very similar is that the zinc band and the wood side structure are identical for first nearest neighbors, and only for larger nearest neighbor numbers start to deviate. So I think that can motivate why they're kind of similar. Now, why it doesn't change very much if you go from, you mean from a bulk material to a surface or to a nanocrystal?
No, for a nanocrystal,
Yeah.
the presence of the surface is quite different for the wood side versus the zinc band. I think that maybe
Right, so that can certainly happen if you look at a specific surface and you would compare, let's say for instance, different surface orientations to a bulk spectrum, that would differ. But the spectra I showed for those nanocrystals, in some sense you can see those as an average over all the surfaces because we calculate the explicit nanocrystal, right? There's no, this is the actual simulation cell basically. And so you would then probably average over those, and I guess my guess is that in that case it doesn't matter as much anymore because that stuff averages away and you get again this idea that the first nearest neighbors are similar in bulk, in both bulk structures, and then you have to go to larger lengths to see a difference. Yeah. But it is true that at higher energies there is a difference between the two. Yeah, go ahead.
Mine's more of a general question because you ended with this challenges for predictive
Yes.
materials design.
Yeah.
So what do you think are the biggest challenges for including excited electronic states in a high throughput sort of capacity?
Right, so I think from my point of view I would say computational cost. So especially here you guys know efforts like the JOES project and similar efforts. That is largely based, not exclusively, but largely based on DFT, and it's tough to do in similar high throughput screening for excited state techniques. It's not impossible, and there are efforts in this direction, but that's certainly the challenge there, right? The cost makes a problem. In some sense, we're trying to avoid that, so we're not really doing a high throughput in my group at all. We're trying to come up with ways of maybe cruder approximations up front to down select from a large database, end up with maybe 100 materials as potential candidates, and then try techniques like this. But cost, I think, I know it sounds like a very trivial answer, but cost is a big challenge.
Thank you everybody for coming.
Thanks.
Let's thank our speaker again.